In this video, we'll explore a competitive learning model. This video was produced in Korean and then translated into English. The audio was generated by AI text-to-speech. In the second video in this series, we looked at weight decay in Hebbian learning. The competitive learning model we'll explore in this video is a variant of this. Let's take a look at the instar learning rule and the competitive learning rule. The competitive learning rule finds a winner neuron and updates the weights connected to that neuron. We will look at how to find the winner neuron and update its weights. And we will implement a competitive learning model for clustering. As seen in this video, Hebbian learning with weight decay, proposed by Stephen Grossberg in the 1960s, is as follows. Each weight in this network is updated by this rule. This is the instar learning rule, a variant of Hebbian learning. For example, W23 is updated by X2 and Y3 as follows. If yi is 1, the weight is updated in this way. And if yi is 0, the weight is not updated. If only one neuron in the output layer or competitive layer fires and the rest do not, this rule can be written as follows. A model in which neurons in the output layer compete with each other to elect the winner, and only the winner fires, is called a competitive learning model. Since only the Y value of the winner neuron is 1, the weights connected to that neuron, marked in red, are updated by this rule. Since the Y values of the remaining neurons are all 0, the weights marked in green are not updated by this rule. In other words, only the weights connected to Y2 have the right to be updated for a given input pattern X. Other weights are not updated for that pattern. The winner takes it all. These are the rules of competitive learning. This can be used for tasks such as clustering. Next, let's take a look at how to find the winner neuron. Let's take a simple network like this as an example. Let's assume the weights are as follows. And we have 2 data points. The first data point has the following features. The first and third features are large, and the second feature is small. The second data point is the opposite. The second feature is large. When we input each data point into this network, we want to select a winner among the neurons in the output layer. The first way is to consider the neuron with the largest activation value as the winner. When the first data point is input, the activation value of the first neuron in the output layer is calculated as follows. It gives us 1.29. The activation value of the second neuron is calculated as follows. It gives us 0.33. Since the activation value of the first neuron is greater, the first neuron is considered the winner. Then the first neuron fires, and it inhibits others from firing. That is, when the first data point is input, only the first neuron fires. Next, let's input the second data point into this network. When the second data point is input, the activation value of the first neuron in the output layer is calculated as follows. It gives us 0.32. The activation value of the second neuron is calculated as follows. It gives us 0.76. Since the activation value of the second neuron is greater, the second neuron is considered the winner. Therefore, the second neuron fires, and it inhibits others from firing. That is, when the second data point is input, only the second neuron fires. This can be used for clustering. When data points with similar features to the first data point are input, only the first neuron is activated, so they can be assigned to cluster 1. Data points similar to the second data point are assigned to cluster 2. The code to obtain the activation values of each neuron can be written as follows. The second approach is to consider the neuron with the shortest distance between the input pattern and its weights as the winner. The distance between the first data point and the weights connected to the first neuron in the output layer is calculated as follows. It gives us 0.14. And the distance between the first data point and the weights connected to the second neuron in the output layer is calculated as follows. It gives us 1.22. Since this distance is shorter, the first neuron is the winner. This means that this weight vector is more similar to the first data point. Let's see why we use similarity to select the winner neuron. The formula for updating weights in competitive learning is as follows. As we saw in detail in this video, this formula means that W is the moving average of X. That is, as learning progresses, W becomes more and more similar to X. Therefore, it is reasonable to select as the winner the neuron connected to W that is more similar to the input pattern X. Next, we compute the distance between the second data point and the weights connected to the first neuron in the output layer as follows. The result is 1.17. The distance between the second data point and the weights connected to the second neuron is 0.17. Since this distance is shorter, the second neuron is the winner for the second data point. The second method is widely used for clustering. This method is similar to k-means clustering. And once training is complete, each weight vector becomes the center of each cluster. The code to find the distance between data points X and weights W can be written as follows. Next, let's look at how to update the weights. When the first data point is input into this network, the first neuron in the output layer becomes the winner. Here, the neuron with the largest activation value is considered the winner. Update the weights connected to the winner neuron, marked in red. If we use this formula to calculate the new W11, we get 0.75, We set the learning rate alpha to 0.5. That is, W11 is updated from 0.7 to 0.75. Updating W21 and W31 in the same way will result in 0.1 and 0.85 respectively. Then the first column vector of matrix W is updated as follows. The second column vector remains unchanged. The code to calculate this could be written as follows. W11 becomes a little more similar to the first feature in this data point. W21 is already the same as the second feature, so it doesn't change. W31 becomes more similar to the third feature of this data point. In this way, the weights become more and more similar to the input data points. This is equivalent to the k-means clustering algorithm, where the average coordinates of data points assigned to the same cluster become the center of the cluster. When the first data point is fed into the updated network, the first neuron becomes the stronger winner. When the second data point is input into this network, the second neuron is still the winner. Next, let's update the weights when the second data point is entered. For this data point, the second neuron is the winner, so we update the weights connected to this neuron, marked in red. If we update these weights in the same way as we did in the previous slide, we get the following results. This time, the second column vector of matrix W is updated. When the first data point is input into this network, the first neuron is still the winner. Next, let's implement a competitive learning model for clustering. The data we will use is like this. Let's use a competitive learning model to cluster these data points into 3 groups. The number of data points n is 1500. The number of features, i.e. the number of neurons in the input layer, is 2. The number of clusters, i.e. the number of neurons in the output layer, is 3. And the learning rate is set to 0.01. Write a function that selects a winner neuron in the output layer. We consider the neuron with the shortest distance between the input vector x and the weight w as the winner. Next, we write a function that uses this rule to update the weights connected to the winner neuron. Randomly initialize the weight matrix. Now we read the data points one by one to find the winner neuron and update its weights. And we use the distance between this data point dx and the weights connected to the winner as the error of this model. The shorter this distance, the better the model's performance. It is widely used to evaluate the performance of unsupervised learning models. Repeat this process 10 times. Next, we predict the cluster index for each data point. We feed the data points into the trained network one by one and find the winner neuron for each data point. The winner then becomes the cluster index for each data point. Finally, we visualize the clustering results. Again, the weights become the centers of each cluster. The results are as follows. Errors decrease during training. The clustering results are as follows. The data points marked in purple belong to cluster 0. The data points marked in green belong to cluster 1. And the data points marked in red belong to cluster 2. And the centers of each cluster are as follows. We can see that using a competitive learning model, we can obtain results similar to those of the k-means clustering model. Let's run this code. We got the following results. Next, let's cluster the NIST images. This code is very similar to the previous one, so let's just check the results. The clustering results are as follows. The images in the first column are the centroid images of each cluster. And the images around this centroid are as follows. You can see that similar images are grouped together. Let's run this code. We got the following results. In this video, we looked at the competitive learning model. In the next video, we will take a look at the self-organizing map